Welcome back. Two fundamental data structures are arrays and linked lists. Most other data types are actually just specialized implementations of these concrete types. Today, we'll look at arrays. An array is like a row of containers. Each container is referenced by its position, starting at 0 and incrementing. Arrays have two major advantages. Random elements can be accessed with essentially constant speed, and looping through them can be incredibly fast. A little more on that second point. Elements of an array are stored directly next to each other in memory. When we access a memory location, the CPU grabs the whole page and caches it. This means that accessing nearby locations in future will be significantly faster. Arrays have the disadvantage of having fixed size. If we try to fill an array beyond its capacity, the best we can do is make a new array and copy elements over. This is about as efficient as it sounds. Let's code up an array class. We'll be using generic programming here. It's really not as scary as it sounds. When we create an array, we want to specify what sort of object we're storing and how big we want the array to be. Our fundamental operations will then be adding and searching for elements. Under the hood, we'll need a pointer to the location where the data is stored and a variable to track the size of the array. We're using the size t type. It's an unsigned integer, usually with 64 bits of storage. Before we implement the code, let's code up a skeleton of how the array will be used. We'll make an array to hold 5 integers, then play around a bit with a few operations. Note that these operations will resize the array beyond its capacity, just for fun. Now let's implement the code. Typically, we'd have a header and source file. However, due to an idiosyncrasy in the way templates work, we'll have to declare the full source in the header. This is because templates are an instruction to make a class, and the code isn't constructed until the class is instantiated. For this reason, our main file needs to see all of the code. It must be accessible from the include. In the constructor, we use Malloc to allocate a chunk of memory to hold our array. You may remember Malloc from a previous video in the series. In the destructor, we simply call free to free the memory. The only edge case to handle on adding elements is a size overflow. We can use realloc to reallocate the memory chunk. If a copy is needed, this is run behind the scene. It can be mathematically proven that by doubling the array size every time, the time complexity will average out to constant time over the long run. This concept is called amortized time complexity. We'll look at it in more detail later. When getting elements, I'm going to take the modulus of the index to ensure it's in a valid range. This is just one approach of many. Actually, I could have said that about any part of this implementation. And that's it. Admittedly, it does take a bit of fiddling around to get this stuff to work, but the payoff is sweet, and we learn things along the way. For instance, it looks like the compiler is using the smallest possible integer as a default value for newly allocated memory. Now, the standard template library of C++ actually has its own version of the array. So for homework, I'd recommend you looking into the std_array class thing. Anyway, all the best, and see you next time. Anyway, all the best, and see you next time.